Today's introduction is to sequences. Now, you've already studied sequences back in Algebra 2. You've studied finite sequences. In fact, this one right here is called a finite sequence. Now, why is it called finite? Because it stops. This one right here is called infinite. Or, if you've ever seen the movie Three Amigos, they would call that infinite. Actually, they were talking about the word famous and infamous, but they said it was being infamous. That you were so famous that you were infamous. Never mind. Okay. Funny movie. Probably doesn't have all the appropriate things for kids. All right, now. So anything that continues on forever and ever is infinite. Everything that stops is finite. A sequence, however, is just a list of numbers. That's all. List of numbers. Now, sometimes those numbers have a pattern that we can find, and sometimes they don't. Obviously, you can see that the pattern for number 1 there is adding 5 every time, or you can say it's a multiple of 5, whereas the second one is a power of 2. Obviously, the third one is going to be things like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and it's going to continue on and forever and ever and ever using that pattern 1 over k. Now, pay attention to this notation right here. This notation right here means the first term. It's the lowercase letter a with a subscript of 1. Obviously, that means the next one would be the second term, and then the third term, and so forth. They have a subscript k. They call that the kth term. Now, all that means is that somewhere out there in the list, so the one after it would be a subscript k plus 1. So the one before it would be a subscript k minus 1. So the kth term is somewhere in the list. The one before it would be a subscript k minus 1, and the one after it would be a subscript k plus 1. All right, so that notation needs to be understood. I would say that there are things that we're going to be adding from what you learned in Algebra 2 last year, but 75 to 80% of what you're going to be doing in sections 9.3 and 9.4, you did it last year. So this shouldn't be a terribly new thing to you. I know that you struggled with it just because there's lots of formulas. Yes, you're going to get every single one of those formulas. Nobody's ever going to take those formulas away from you. I know that was the next question on your mind. Find the first 6 terms and the 100th term. Okay, so the first 6 terms. So all I'm going to do is plug in a 1. 1 squared minus 1, so I got a 0. The second term, 2 squared minus 1. 4 minus 1 is 3. The third term, 3 squared minus 1. 9 minus 1 is 8. What you basically are seeing is a perfect square take away 1. Right? You had 1, 4, 9, right? If you looked at your perfect squares, 1, 4, 9, 16, 25, 36, as I go throughout my list, the fourth term is 4 squared minus 1. So, yeah, it's going to be 15. And the next one's going to be 24. The next one's going to be 35. Right? Because I'm just doing that same thing. Now, there's a lot of terms. Somewhere out here is the 100th term. How am I going to figure that out? Same way we figured out the other ones. A sub 100. 100 squared minus 1. Well, that's 10,000, right? Because there's 4 zeros and a minus 1, so 9,999. That is a horrible looking 9. Sorry about that. My apologies to all 9s in the world. Okay, didn't mean to offend. Not to be confused with the 9s from Germany, because those are a bunch of no's. Oh, let's see here. Now, there are 2 different types of formulas to work with. Explicit formulas and recursive ones. Recursive formulas are only going to be used to find the first 5 terms. After that, folks, I am not using the recursive pattern again. I want to use the explicit pattern. Because the advantage of the explicit formulas, right here it says they're easiest to work with. The reason is because you can go to any value you want. You can find any term quickly. I cannot spell G-Money Christmas. That's horrible. Quickly. We're going to see here from this example, recursive are great for the beginning, horrible for later. Here's why. A recursive pattern is made of 2 parts. It has, and usually I put like a bracket on the side, it says something like this, b sub 1 equals, and then it has to have a starting point, okay? We have to have a starting number, otherwise we don't know where to begin. Okay? Now let's look at this notation that you see here, b sub n. What is that? Some term. We'll call it the next term. Where is b sub n minus 1? Well, remember a little while ago I was talking to you and I said with the a sub k stuff, and we talked about how, we got, any old term, and a sub k minus 1 would be the previous term, the one before it. So we're going to use that concept here. So this represents the previous term. Please make note that that little subscript is n minus 1. So many of you write your notation and that little minus 1 is not in the subscript. You think it's a giant minus 1. I'm like, no, that means something completely different. So the next term is equal to the previous term, and then it tells me what to do. So either it's going to tell me to take the previous one and multiply, or the previous one and add, or subtract, or divide, or something. I'm going to take that previous one and do something to it. In this case, they're telling me to add a number. But this could very well be something like multiply by a number, or subtract a number. Lots of things could be done to that previous number to come up with the next one. Okay, so if I do this by hand, we're going to start with a number 3, because that's where they told me to start. And according to this, it says that the next term is the previous one plus 2, plus 2, plus 2, plus 2, plus 2. Now, don't ask me to find the 100th term that way, because I'm going to get sick and tired of that pretty doggone quickly. This is where we need an explicit formula. Now, what we're dealing with right here is actually a very specific type called an arithmetic sequence. This is what you discussed and talked about last year, arithmetic sequence. An arithmetic sequence is based upon adding. Now, I hope that you all know that you can still add a negative number. Adding a negative number is called subtraction. But we add a common difference. Add a common difference. Now, how do you find a common difference? If you're looking at terms like this, you take any term you want and you subtract the previous term. Now, we actually use a letter for that. We call that the common difference, D. We use D for difference. I'm pretty sure you already knew that, but figured I'd throw it in just for kicks and giggles. Now, the arithmetic sequence, so the recursive pattern for an arithmetic sequence, which we talked about last year, looks like this. So I'll use T's just for fun. Sorry, keep using the term. And I don't need to use the same term over and over and over. T sub n equals T sub n minus 1 plus D. So this is the recursive formula for an arithmetic. So this, now I'm going to come over here and do the explicit. Now, what kind of shape do you get when you so the first term gave me what? 3. And the second term gave me 5. And the third term gave me 7. Well, what I'm hoping that you see, and it would be better off if I used Desmos, is I'm hoping that you're seeing a linear function. And if you're dealing with a linear pattern, then your explicit formula is going to look like a linear function. Now, I know you're all going to say, well, is that y equals mx plus b? You can write it like that. I'm going to write it in the point slope version. Now, as a reminder, point slope kind of looked like this, y minus y1. Not kind of, it looked exactly like this. M times x minus x1. I'm gonna modify it a little bit. I'm going to take this term and move it to the other side, and so it would look like this. So you're saying, well, how does that relate to the notation of these functions? Well, it's going to look a little bit like this. A sub n equals a sub 1 plus the common difference d times n minus 1. So, just as a walk down memory lane, hopefully you get the idea in your head that the slope of the line and the common difference are the same. Hopefully you understand that the y1 and the first term are the same. And because we're talking about the first term, that's why I know I can put a 1 right there. So, what's it going to look like for my example for this particular question? Okay, this particular question, a sub n equals, first term was 3. With a common difference of 2. All I'm doing is plugging in values for the first term and the common difference. Okay. So they're asking me for the 100th term. That's not too hard to do with this particular formula. Don't ask me to sit there and add 2 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 until I get to the 100th term. Ain't no way I'm doing that. But, and don't you dare be the kid that says 3 plus 2 is 5. Oh, that's painful, folks. Painful. We got 2 times 99. That's good old 198. 3 plus 198. Just follow the order of operations. I mean, even if you just type this thing on a scientific or graphic calculator, it will follow the order of operations for you. But 201 is what we should end up with. Now, I do want to flip over on my camera, and I don't think my camera's ready, so let me get my camera ready. All right, so I got my calculator. I do want to show you something on your calculator. The recursive formula is, your calculators, scientific or graphing, are all set up to do the recursive pattern extremely easily. So, for instance, you can take a 3 and enter it. Let's say this was my starting value. I'm going to go with the last sequence like we did. Okay? Now, if I want to tell the calculator to take the last value and add 2, which in that case was our common difference, I'm going to do this. I'm going to type plus 2. You notice how it takes answer plus 2? So this is the recursive pattern. When you hit enter, guess what? It gives you the second term. When I hit enter again, it gives me the third term, and the fourth term, and the fifth term. See, all I'm doing is using this recursive idea to go back and repeat to find more terms. So your graphing calculator is set, but I am not going to sit there. If you're going to do that during a test, if you're going to sit there and go, oh yeah, let's see, 6th, 7th, 8th, 9th, 10th, 11th, 12th, eventually I'm going to get to 100, right? I'm going to get to the 100th term if I just keep doing this, okay? I will walk over by your desk while you're doing this, and I will start shouting numbers in your ear until you lose count and have to start over. That's right. I don't give any credit to this. If I'm asking you for the 2000th term, you know, all I have to do is change the number, make it a larger number of terms that you need to figure out, and you won't want to do it. But if you try to do it, which I know that there are some of you who are tempted to do that because you just want to be disagreeable, you're going to lose all credit. So good luck with that. All right, now, back to our regularly scheduled programming. So, recursive, explicit. Those are the recursive and explicit formulas for an arithmetic. Eventually, we'll get to the geometric ones, the ones based on multiplication. Now, we get to the part of pre-calc here that you know wasn't in Algebra 2. Limits, right? Your favorite thing in the whole wide world. A limit, as I want to remind you, is a y value. Please, 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 please understand that. A limit is a y value. Over and over and over again, I try to get that through your minds. Limit is a y value. Okay? And you'll notice that we're taking the limit as n goes to infinity. So the n being the, you know, first term, second term, third term, fourth term, fifth term, the number of the term is getting larger and larger and larger. Now, if the y value is a finite number, if we're getting closer and closer and closer and closer and closer to a finite number, then we say that the sequence converges. Converges means gets close to a single number. As opposed to not getting close to a single number. Now, there's a couple different ways that can happen. You could bounce back and forth between a 1 and a negative 1, and a 1 and a negative 1, and a 1 and a negative 1, and a 1 and a negative 1. I've seen sequences like that, and I've also seen sequences that click closer and closer to positive infinity. If those things happen, then it diverges, okay? And I know some of you are saying, diverges? Isn't that when you really want to jump into the swimming pool? No, folks, it's more than that. Diverges means, that poem, that Robert Frost poem, two sequences diverged in the woods, and I took the one less traveled, and that has made all the difference. Diverges, not getting close to a single number. Determine whether the sequence converges or diverges. Okay, let's look at A. We got 1, 1/2, 1/3, 1/4. So what you should see if you were going to graph this is 1, 1/2, 1/3, 1/4, and you should see that we're getting closer. Are we ever going to get to 0? I hope you know the answer is no. So is this converging? Sure. Take the limit as n goes to infinity of 1 over n. We've talked about this before. We've talked about how it's getting closer and closer to 0. It's converging to 0. Well, what about the next one? Okay, so we got 2, and then we've got 1.5, and then we've got 1.33, and then we got 1.25. So notice that the number on top is n plus 1, and the number on the bottom is just n. Okay, all right. Now, how did I get n and n plus 1 and n? Remember, you're plugging in a 1 to get this. You're plugging in a 2 to get that. You're plugging in a 3 to get that. You're plugging in a 4 to get that. So that's how I decided what the numerator and denominator would be. I remember teaching you when we did the rational functions that if you take the largest power of n in the top and the largest power of n in the bottom, you would know what's happening when you take the limit of this fraction. What is it? Yes, it's converging to 1. Converging to 1. If you look at the next one, though, you're starting at 2, and then you're going to 4, and then 6, and then, oh my goodness, it's just continuing on out into the universe, never stopping. So that one right there is diverging. Right? So part C is diverges. D is the one I mentioned earlier. You're starting at -1, and then +1, and then -1. So you're literally bouncing back and forth, above and below, above and below, above and below, forever and ever and ever. You never get close to a single number. So D also diverges. I'll just use the ditto marks. It diverges. It's not getting close to a single number. Was that example 3? Whew, man, we're zipping through this. All right. Determine whether they converge or diverge. I'm hoping, all right, so I'm hoping that you're going to say, okay, we're taking the limit as n goes to infinity. Same thing for the next one, limit as n goes to infinity. Don't know why they didn't write this notation, limit as n goes to infinity. Okay, and we talked about how we would do this. Largest power of n in the top and the bottom. What does it give you? If it reduces to a nice number, which it would reduce to 3. What about this one right here? That reduces to 5 over n because you can cancel out n squared from the top and the bottom. Well, n is getting bigger and bigger and bigger and bigger. Remember, I'm taking the limit as n goes to infinity of this. Well, that means it's getting closer and closer to 0, right? Because the denominator is continuing to get larger, but the top is staying the same. Well, what about this one? Largest power of n in the top and the bottom. If I reduce that, I get n. So what's the limit as n goes to infinity of that? Well, folks, what is this producing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's not stopping. Diverges. Whoa. Almost lost my V. All right. Next on the list. So we've already talked about this a little bit, okay? Because the first one of the previous examples was about arithmetic sequences. Now, I'm not a big fan of the way they have written things. If you take a look at the way they have written their notation, all right, you know, I wrote a sub 1. I called this a sub n equals. They like to throw the n minus 1 in front of the d. Nah. We'll put the d in front. So I don't know why they write it in that form. I think there's a reason in one particular example of why they're doing what they're doing. But now I do see something that's important to you, and it's going to become important in other examples. So to go from the first term to the second term, you add one of the constant differences. But if you were to ask me to jump from the first term to the third term, well, that's like taking 2 steps. You know, if I have 2 different numbers and you ask me to jump to the third one, then I have added the common difference twice. So that's why they called this a sub 2d, or a plus 2d. I'm sorry. And if I were doing it, I would write a sub 1 plus 2d. That would be the way I would write it. So let's suppose I wanted the, let's see, third, fourth, fifth, sixth term. Well, how many constant differences did you add? 1, 2, 3, 4, 5, 6. So this would be a sub 1. Is that right? Did I go 1, 2, 3, 4, 5, 6? Oh, that's actually the 7th term. So the 7th term that I had listed out here was a sub 1 plus 6 of those common differences. Now that's going to come up in some of the examples where they have missing terms, and we'll talk about that when we get there. I notice when they wrote their recursive pattern, if you look at this right here, what's noticeably missing is they didn't write down the starting point. I think that's kind of dumb. And I also want to highlight this to you. Notice where I put the blue box. There is this extra thing here which is mathematically correct and technically needed, but I'm not going to require it of you. What it tells me is that the rule doesn't apply to the first term. Okay, so rule only applies to second term and beyond. If we called him Deuce Lightyear, to second term and beyond, instead of Buzz. Anyway, weird mind, weird thoughts. Can't explain it. Defining arithmetic sequences. Okay, so we are going to get into some arithmetic sequences here that look different. Now the first one looks exactly like what you'd have seen in Algebra 2. For each of the following arithmetic sequences, find the common difference. Like I said, pick any term you want. Say I picked a positive 6, and I wanted to know the common difference. I subtract the one before it. So I know that we are adding 4 every time. Then it says find the 10th term. Okay, well, I mean, literally we have the 5th term, and going to the 10th term is not that difficult, so why couldn't I just say, okay, the 5th term was 10, and we're adding 4, so 6th term, 7th term, 8th term, 9th term, 10th term. So it's 30, okay? That would not be a drastic need for some sort of formula, but it would be nice if I knew how to do the formula, right? So let's just do the formula, and then we'll plug in 10. So first term plus Common difference, well, we know the common difference is 4. We already know the first term is -6, right? We got that from here. Times n minus 1. So there is actually part D of this. Sorry, I'm getting myself out of order. The 10th term, which is part B, we already did A, would, 10th term could be plugged in. I want you to use that formula because I'm not going to ask you for the 10th term. I'm going to ask you for the millionth term. Something like that, something crazy. So 4 times 9 is 36, and 36 plus -6 makes 30, which is exactly what we found when we looked at the calculator. They also asked for the recursive formula for this, and the recursive formula for this, let's see here. We want the first term, then we want the rule to find the next term. The next term is equal to the previous term plus 4. Now, I have seen in the notes, and I need to make this mention to you, that sometimes they like to write their notation a little bit differently on their recursive functions. Do you realize that you could write it like this? A sub 1 equals -6. What if I called a sub n plus 1 the next term? Then what would be the previous term? Now remember in our list we said that a sub n, and then you have a sub n plus 1, and we had a sub n minus 1. So if you call this one the next term, what would be the previous one to it? A sub n. I have seen that notation showing up in the homework, and I wanted to make mention of it to you so that you understood it's not really any different. They just shoved over the notation from one place to the next. Okay, now, next example is a little bit different. Okay? If you want to know the common difference, you take any term, natural log 6, and subtract the previous term. Okay, this is where Beyonce comes in and she's like, all the single logs, all the single logs. Okay, because we've got to get a single log. And what are we going to do with the 6 and the 3? Of course, we're going to divide them. Why didn't I write? There we go. So the common difference in this is the natural log of 2. I know, pretty cool. It's not just, and I'm not going to type that on a calculator. All right, there's no reason I'm going to type that on a calculator. We're just going to include it in our formulas. So for instance, let's see here. Let's jump to this. So that's letter A. Let's jump to letter D, the explicit one, right? So that would be A sub n equals first term. Yep, there's your first term. Plus common difference times n minus 1. Okay. Keep in mind it's the natural log of 2 that's all one thing. It's not, you can't separate the natural log into 2. Wouldn't want you to try that at home or anywhere else. If I wanted to know part B was the 10th term, then yes, I'm going to plug in 10, right? 10 minus 1. So 9 times the natural log of 2. Ooh, what if we did 9 times the natural log of 2 plus the natural log of 3? Ooh, what if we required you to put that into a single log? Ooh, yeah, that's a good idea. I like it. Because single logs all have coefficients of 1. Clearly, this has a coefficient of 1. Clearly, this does not. So what are we going to do with that 9? I hope you were saying, well, King Julian would tell me to move it. Because we like to. That's right. Natural log of 2 to the 9th plus natural log of 3. Oh, 2 to the 9th. Let's see. 2 to the 11th is 2048. That's that famous game, right? And then so 2 to the 10th would be 1024. That's 512, isn't it? So we have the natural log of 3 plus the natural log of 512. I want to double check that in my mind because I just want to make sure that I'm not crazy. Yes, I got it. All right, now, what can I do with those two numbers? Because, as Beyonce would say, make it a single log. So that would be the natural log of 3 times 512, right? 3 times 512. So like 1536. That's the 10th term in my list. That is so cool. I like that question. Okay, then they ask me for a recursive pattern. Okay, we can do the recursive pattern, right? It has to have a starting place. So the first term is natural log 3. And the next term is equal to the previous term plus, now the common difference here is not just a number, not just a normal number. It's pretty cool, right? Natural log, what was it, natural log 2? Now I'm putting it in parentheses. Those parentheses aren't the most important thing in the whole wide world. I only did that because I didn't want you to think that, I want you to remember that the natural log of 2 is one number. Yeah, I can type natural log 2 on my calculator and get some weird decimal, but I don't need a weird decimal when I can leave it as natural log 2. That is an awesome question. I love that. Talk about combining what we did last year with what you've done this year and your logarithms. Ooh, that's good stuff right there. And we are at the end. We need to pick up with geometric sequences when you get to class tomorrow.